One can estimate the heat of reaction for any reaction from bond energies. Okay, anytime you talk about heat of reaction, delta H reaction, you remember that enthalpy is a state function. It doesn't matter how you get from the initial state to the final state, doesn't matter the path. So again, we're going to pick a way that's convenient to us for getting from reactants to products and calculate the delta H. What we can do is we can take a reaction like this, which we would normally write as CH4 plus F2 going to CH3F plus HF, but I've written it this way so that you can see all the bonds that are present, because what we're going to do is we're going to break apart all these reactants and products into separate atoms. It's not writing. Okay, when we calculate heat of reaction from heats of formation, we take all the species to elements in their standard states, which aren't necessarily separate atoms. Hydrogen in its standard state is H2. Okay, but let's take them into their standard state, or into separate atoms. And if that's true, in methane, CH4, then we are breaking 4 CH bonds. So the energy of going from this reactant, methane, to separate atoms is 4 times the bond energy of a CH bond. And when we go from fluorine to separate atoms, we have 1 FF bond, so that's the bond energy of a fluorine-fluorine bond. So bond energy, as you may recall, is the energy it takes to break a bond. So now if we're going to go from these separate atoms to the products, we have to form bonds. So the energy of going from a separate atom to CH3F, you're going to form 3 CH bonds and 1 CF bond. So that one is going to be the opposite of the bond energy. So we have to say the negative of the bond energy, because the bond energy is breaking. The bond energy is CF minus 4 times, or so 3 times. Let me get rid of that. It's going to be minus the bond energy of CF and minus 3 times the bond energy of CH. And then going from separate atoms to HF is going to be 1 times negative bond energy of HF, because you're making 1 HF bond. Here you're making 3 CH bonds. So that's how we can estimate it. We break all the bonds. And since bond energies are defined as breaking bonds, then we end up with a heat of reaction that's equal to the sum of all the bond energies of the reactants minus the sum of all the bond energies of the products. Now remember, for heats of formation, the heat of reaction is the sum of heats of formation of products first minus reactants. That's because of how they're defined. Bond energies are for breaking bonds. Heats of formation are for forming compounds. So they're opposite. All right, so in this, we actually can simplify it a little bit by realizing that these 3 CH bonds do not have to break. So we actually don't have to break all of them. We can just break the 1 CH bond, which will become the CF bond. So we can ignore these, keep them intact, and make things a little bit simpler. So we're going to say the heat of reaction is going to equal, and we're going to break this bond. We're going to break this bond, and we're going to form this bond, and we're going to form this bond. So the heat of reaction is the bond energy of 1 CH bond plus the bond energy of 1 fluorine-fluorine bond minus, and I'll put the products in brackets, the bond energy of CF plus the bond energy of HF. And this is a plus because I put the minus outside of the bracket. All right, so we can get those numbers by looking them up on a table of bond energies. The bond energy of the first one is 113 kilojoules. Bond energy of fluorine is 159 kilojoules. Bond energy of CF is 485 kilojoules. And the last one is 567 kilojoules. So when we combine all these, we get 572 minus 1052, which gives us a heat of reaction of negative 480 kilojoules, which is exothermic overall because it's negative. All right, so now I want you to try solving a problem where we use bond energies to calculate the delta H reaction for this reaction. Or actually, I will show it for you. You can stop it if you want to try it yourself. But what we need to emphasize is in order to do it, you have to actually draw the Lewis structures for the bonds. You can't just assume what they are. And when you draw a Lewis structure for nitrogen, you get a triple bond. Okay, so that's important to note. And for hydrogen, you have 3 of these. Because the coefficient is 3, you have 3 hydrogen-hydrogen bonds, and you're forming ammonia, which looks like this. But you have 2 of them, so I'm going to write them both out. That way you won't mistake how many bonds you really need to break and how many you really need to form. Okay, so looking at that, our heat of reaction is going to be the bond energy of a nitrogen-nitrogen triple bond, and that would be different than a single bond. That's why it's important that you draw the Lewis structure and realize that. And then plus 3 times the bond energy of a hydrogen-hydrogen bond, minus, and I'll put all the products in brackets, and it'll be, there's 3 hydrogen-nitrogen bonds in each ammonia, a total of 6. So we have 6 times the bond energy of nitrogen-hydrogen bond. All right, and then if you look them up on a table of bond energies, which any standard text will have, you'll see that nitrogen triple bond is a lot of energy to break. 945 kilojoules. To add to that, 3 times the bond energy of hydrogen, which is 432, minus 6 times the bond energy of NH, which is 391. And when you add them together, you'll get negative 105 kilojoules, which is an exothermic reaction. And that was 105. All right, so here is a table of bond energies that we use to solve these. It looks something like this. And there's usually a section for single bonds, and there's a section for multiple bonds. Here's the nitrogen-nitrogen triple bond, 945 that we used. There's also a double bond for nitrogen, and there is also a single bond. So make sure you pick the right bond, whether it's double, single, or triple bond, because the energies vary greatly. All right, so you can use that now to calculate one for yourself. You should definitely try this yourself before restarting the video. Calculate the heat of reaction for C2H2 plus hydrogen going to C2H6. And actually I've given you, okay, you're going to do this 2 different ways. You're going to use the heats of formation for it, and you're going to use bond energies and calculate it 2 different ways and compare them. All right, so heats of formation, I'm going to go back and review. Heats of formation, calculate heat of reaction by taking the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants, and they each get multiplied by the right coefficients. Okay, for this, we have the heat of formation of the products, C2H6, so that's negative 85. These are all in kilojoules per mole. and we subtract the heats of formation of the reactants. C2H2 is 227. Hydrogen is an element, so that is 0. And so your answer is negative 312 kilojoules per mole. Using bond energies. Okay, now we will calculate the heat of reaction for the same reaction, but this time using bond energy methods. So in this case, the delta H for the reaction is given by the sum of the bond energies for the reactants minus the sum of the bond energies of the products. Okay, so you have to be able to draw the Lewis structures, and the Lewis structure for C2H2 has a carbon-carbon triple bond and 2 hydrogen atoms. Then 2 H2s is 2 HH molecules. And those react to form C2H6. I won't draw the H's on there, but there's a H on each of those lines. And then you can see that the heat of reaction is then given by we have to break one carbon-carbon triple bond, which is 839 kilojoules per mole. And we add that to 2 hydrogen-hydrogen bonds, which are 432 kilojoules. Then we subtract off the products. In the products, we have 1 carbon-carbon single bond plus 4 times a carbon-hydrogen bond. Because remember, we didn't break 2 of them, we're just forming 4 of them. Okay, and you work out the math, and this comes out to negative 296, and remember the units are given here in the chart, kilojoules per mole. Okay, now let's look back at the heat of formation value, which was negative 312 kilojoules per mole, and this one is negative 296, so they don't give the same number. You have to remember that both methods, heat of formation and bond energy method, are approximations to the true heat of reaction for this reaction. They're both methods of getting close to the real answer. So neither one of them is exact. However, the bond energy one is actually considered less accurate, and the reason for this is that the bond energies given in charts are really averages of those bond energies over many different molecules. So they're not exact bond energies for these specific molecules in this reaction. But anyway, both of them give an approximation. Obviously, the right answer is somewhere near negative 300 kilojoules per mole. And they are both useful tools.